So here's our first one. We've got cotangent squared equals 3/2 cosecant theta. And because I haven't actually showed you how to do this one yet. That'll be why. So we're going to go through these today, these really weird ones. So when we're on the interval, we're looking for just our values in the unit circle. So we're going to just have a very limited number of answers. But when we have a couple of trig functions like this, especially when one of them is squared, that was not the laser pointer. When one of them is squared, I want us to think about, can we get these two pieces to have the same trig function? Do we know any relationship between cotangent squared and cosecants? Yeah, one of our trig identities is actually that 1 plus cotangent squared equals cosecant squared. That was a weird. I got it. Cosecant squared. So we can use that. We can use that to replace our cotangent squared with cosecants. So I can come in here and say, well, I know cotangent squared is actually the same as our cosecant squared minus 1, using that trig identity over here, this guy. And right now it's still equal to that 3/2 cosecant theta. So at the very least, that gets it to where we have the same trig function. We like that. That makes things easier. And then I look here and I go, ew, there's a fraction. Gross. I'd really rather not. How can I get rid of that fraction? Multiply by 2. I'm going to multiply this guy by 2 because I would really, really, really rather not have to deal with the fraction. But since I multiplied the right side by 2, we got to get the left side by 2. Because fractions are gross. So we're going to have our 2 cosecant squared theta minus 2 equals 3 cosecant theta, which is better.
What do you want by itself again?
We're trying to get to a theta. Theta equals. So now let's make it so we don't have things on both sides of the equal sign with trig functions. So let's go ahead and subtract our 3 cosecant theta from both sides. We want to try really, really hard not to divide by trig functions because we don't want to wind up losing out on a solution. So we're going to subtract it over, minus 3 cosecant theta. And I'm going to squish this in here, in between, for reasons that we will see here in just a second. So I'm going to write this as 2 cosecant squared theta minus 3 cosecant theta minus 2. It looks so weird, but it also kind of looks vaguely familiar. It's a quadratic. There's a squared piece, a not squared piece, and a just the number. So this is called a quadratic type equation. When we're working with quadratic type equations, we're going to do a u substitution. So I'm going to pick a u that's going to make my life way, way easier, which means I'm going to pick the middle guy every time. So we're going to use our cosecant cosecant theta as our u. You don't technically have to use a u. They're always called u substitutions. When you get into like calculus, you'll want to use the u. But I mean, technically you can use whatever you want. So the reason that's going to be helpful is I can then write this as 2u squared minus 3u minus 2. How could I solve that? Factor it. Factor it. Let's get to a solution for u. I want to know what u equals. So factor this. I don't care how you factor, just that you factor. Factor whatever way works for you. You can factor by grouping, you can use the box, you can use bottoms up, split the middle. There's lots of different techniques. For most of them, we'll need to use this piece where we take our a times c, get our -4, as to be -3. I can figure out those pieces. Here we have our -4 and +1. That splits our middle term. We can factor it by grouping. We can factor it with the box. There's lots of options here. No matter what way we factor, we should wind up with what pieces as factors? What did we get? Careful on our signs. Similar? 2u plus 1 and u minus 2. Be careful, careful, careful on our factoring stuff, okay? I was like, when in doubt, you can always go back to old school. So do the algebra 2 here. This guy with our 2u squared and our -2 and our -4u and our u. When in doubt, write it out. Totally fine. Pull your factors. Again, you don't have to do it this way, but we have our u and our -2 here, and then our 2u and our +1. So if you forget how to factor, there's a very fast example of that one. So what do we get as our solutions? Our roots are zeros down here for u. We get u equals, because we add 2 to both sides, so we get u equals 2. And u equals -1/2. Because we set each factor equal to 0. But we don't actually want to know what u equals. I want to know what theta equals. So we need to resubstitute in our u substitution here. So we want to know when cosecant of theta equals -1/2. And we want to know when cosecant of theta equals 2. I'm going to change the view on the page for a second, just because I need a little bit more space. Some of us will be able to do it from here, and that's okay. And if you can, I love that. Some of us, we're going to have to think it into our sine cosine, guys. Because cosecant is related to which of our trig functions? Sine. So this is 1 over sine. We're looking for when 1 over sine theta equals -1/2. And 1 over sine theta equals 2. For some of us, this will be where we can see it. If not, keep going. Since we're looking at reciprocals here, flip them both. Sine theta equals -2. And sine theta equals, what's this one when I flip it? 1/2. Because this is 2 over 1. So when we take our reciprocal, it's 1/2. So when is sine of theta 1/2? 5 pi over 6. Any other place? And pi over 6. When is sine of theta -2? Never. Everything on the unit circle is between -1 and 1. Think through sine. When we graphed it, our range on sine is between -1 and 1. Sine never equals -2. This does not exist. So this is, it's like an extraneous part over here. It's an extraneous solution. It's an extraneous angle. So our solutions, our answers, our final choices, the only options for theta that are going to give us a solution here are our 5 pi over 6 and our pi over 6. Okay, so sometimes we're going to have to do some u substitution. Sometimes we're going to have to do some factoring. If they were asking us for all possible solutions, not just on the interval, we'd put our plus 2 pi n on our angles down here when we were looking at those. But we were on the interval, so we just took our unit circle values. Okay. Questions on the first one of this quadratic type annoyance? Because they are annoying and unpleasant. And that's normal. Okay. Let's do another kind of kooky looking one. Get our little black box at the top. So here's our next piece. We've got 2 cosine squared theta plus 3 sine theta minus 3 equals 0. What do we notice on this one? I was going to say we've got a cosine squared, I've got a sine squared. We're probably going to need to do a u substitution, or we don't have a sine squared, we have a sine. We have a cosine squared, we have a sine. Going to probably need to aim for a u substitution because this does look like a quadratic. But if I started with a u right now and I set my u as sine, this guy's not exactly sine. Can we make it be a sine? How? What are we going to replace it with? Super close. Be careful, careful, careful. Because remember our trig identity, that's our, there it is. Our sine squared theta plus cosine squared theta equals 1. So if I want to replace my cosine squared theta, it's 1 minus my sine squared. So be careful, don't lose track of our sine stuff, our sines with a G, because it'll mess with our sines with no G. I don't like that they're pronounced the same. So I can replace this cosine squared with our 1 minus sine squared because of that Pythagorean identity. So this becomes 2 times 1 minus sine squared theta plus 3 sine theta minus 3 equals 0. Then what should we do? As I say, it's like you could do your substitution now, but I'm going to simplify first and then do that. Because I've got a set of parentheses here. I'm going to need to do a little bit of distribution. 2 times 1 gives me 2. Minus 2 times sine squared theta gives me 2 sine squared theta plus 3 sine theta. Oh, that was a bad theta. I'll fix that one. Minus 3. Now what can we do? Okay, we've got some like terms. We could do our u substitution right now. I'm going to go like terms, then I'll do that one. But like there are so many different places where you can do a couple of steps at the same time. Just be careful about doing too many at the same time, or you run into problems where we just lose track of what's happening. So now I've got my 2 minus 2 sine squared theta plus 3 sine theta 2 minus 3 gives me a minus 1. What are we going to do our substitution with? What's my u going to equal? Sine of theta. So when I write this, having done that u substitution, it's going to look like minus 2 u squared plus 3u minus 1.
I thought we couldn't have the leading one be negative.
So how can I fix that?
Put it on the other side.
I was like, if you want to absolutely, if you want to add them across the equal sign, totally fine, totally works. You could also, I heard someone else say it. Yeah, divide or multiply by negative 1. It does the same thing as if I added it across the equal sign. So if I plus 2u squared to the other side minus 3u to the other side plus 1 to the other side, same vibe as if I multiply everybody by negative 1. Either way, yeah, because we don't want to have to deal with a minus 2 something squared. Gross. Negatives in front make it so annoying to try and factor it. So multiply everybody by negative 1, add it to the other side. Doesn't matter, change our sign. Or you can just factor out a GCF of negative 1. That is also okay. It's going to give us our 2u squared minus 3u plus 1. Because, yeah, that's gross, icky. I don't want to do it. This now isn't too bad. We can do this. What are we going to do from here? Yeah, we need to factor this thing. So do our x in box, split the middle, bottoms up, whatever way it is that you do your factoring. We want to put this in factored form because we want to try and get to a u equals so that we can get all the way back to what our theta equals. So when we do this and we get our factors, check which one I'm on. There we go. We're going to get our 2u minus 1 and u minus 1. So we get solutions of u equals 1 and u equals 1/2. Substituting back in our u substitution, we're going to have our sine theta equals 1 and sine theta equals 1/2. So what are our options for theta? Where are our solutions going to be here? Yep, because when sine is 1, that happens at the angle pi over 2. And for our sine of theta equaling 1/2, pi over 6 and 5 pi over 6. So just to give us a little bit of clue. So that these two came from this guy. And this one came from this guy, just so we see where those came from. And this is our answer. These are our options for theta. Those are the only options that we have on the unit circle that would do this. Okay. Questions on this one? So we're going to see these quadratic type ones kind of pop up every now and then. There's a couple other kind of weirdly shaped ones that I want us to talk through in 7-2. Okay, so questions on our quadratic type. Let's look at this one next. So again, we're looking for our solutions here. We want to find theta. We've got cosecant theta equals cotangent theta plus tangent theta. So now not only do I have two different trig functions, I've got three of them. Ew. That's a fine option. You can put them in terms of sine and cosine. You can absolutely do that. You can also like put them in terms of cotangents. You can put them in terms of other pieces here. Like there's a lot of options. Putting them in terms of sine and cosine is absolutely valid. So let's do it. Cosecant is the same thing as our 1 over sine theta, right? And cotangent, that's our cosine theta over sine theta. And our tangent is sine theta over cosine theta. One thing we're going to have to be careful of since we're switching everything into sine and cosines right here is that we're going to have to come back at the end and double check. Since our original function is cosecant, we're going to need to make sure that these guys don't wind up undefined up here. Okay, so switching to sine and cosine is an absolutely valid strategy. When we do that, we just need to be really careful about where our answers land. But we'll look at that when we get to the end. But just as a little precursor warning. So now looking at this, it's a little bit messy, but that's okay. We can deal with that. What can we do? Common denominator. I think that's where you were headed, but I just was like, my brain got stuck on it. I was trying to figure out where we were going. So let's simplify this side, because I'd really like it if we weren't doing separate adding and subtracting, because if we have things that are at least being multiplied, then we can try and factor off. Because this is not quadratic, so we're going to have to figure out what else we're doing. So we're going to have our 1 over sine theta. I'm just going to make this a little bit bigger because it's kind of gross. When we get these guys to common denominators, we're going to wind up with sine theta cosine theta as our denominator. What are we going to have in the numerator? Cosine squared theta. Because I need to multiply this left guy by cosine over cosine. And this guy's going to be our sine theta. So we have plus sine squared theta, which I heard a couple of us already notice. What does that do? Makes it a 1. So we have 1 over sine theta. And we want to know when that equals 1 over sine theta cosine theta. Okay, a little less gross already. What can we do? How can I figure out what these thetas are going to be? Yeah. I'd really rather not deal with them in the denominator. Ew. Take our reciprocal, cross multiply, multiply by denominators. However it works for you to think about it, we're going to get our sine theta equals sine theta cosine theta. Taking our reciprocals, you could multiply by our denominators and get over there. If you multiply by denominators, you'd wind up with a slightly different statement, but taking our reciprocals also works. What should we do now? Get everything on one side, because we're going to try really, really, really hard to not divide by a trig function, because we don't want to wind up losing out on a solution. So let's subtract our sign from both sides. So we're going to have that our 0 equals sine theta cosine theta minus sine theta. Still kind of gross, but we're getting there. I promise we're almost there. What can we do next? Down here. What do we notice about these two pieces? Both pieces have a sine. We have a common factor here. Factor out a sine of theta. Sine theta cosine theta minus 1. So we want to get things on one side so we can try and factor it, especially when we have two trig functions like this. So we need to get things not being added and subtracted so that we can factor as much as possible. Because that's going to let us see our options for theta. We're going to look at sine theta equals 0. And we're going to look at cosine theta minus 1 equals 0. So this is the same thing as having cosine theta equals 1, right? What are our options for theta here? And we're looking at our sine. Yeah, because for sine to equal 0, we would either be at angle 0 or, where else is sine 0? Pi. How about for cosine of 1? Where is that going to happen? Sine 0. Oh, so we got the same thing there. Then remember, we didn't start with sine and cosine. We started with cosecant. Are these valid angles on cosecant, or is it undefined? I was going to say, because sine of 0 is 0, right? So that means cosecant of 0, 1 over sine, it's 1 over 0. So cosecant of 0 is undefined. What about cosecant of pi? What's sine of pi? Sine of pi is also 0. So it's undefined for pi as well. Same thing's actually going to happen on cotangent.
Wait, why is pi undefined?
Because sine of pi is 0.
Oh.
There we go. Cosecant of pi is also undefined. And in fact, that's going to happen for cotangent as well, because cotangent also has a sine in our denominator. So both of our values that we find were undefined here. We can't actually have either one of them as solutions for the system. It doesn't work. There's no solution on this one. A lot of work for no solution. So when we have, especially those reciprocal functions, if we choose to go the switch everything to sine and cosine route, totally valid, but make sure we double check that it's not undefined there. You could also do this one by common denominating your cotangent and tangent, then you'd get a trig identity to switch it to cosecants, because you would put it all in terms of cotangents. It's not any better than this one was, so it's why I kind of followed you guys' lead on that one. So when they give us 3 different trig functions, they get a little messy. Try and get us to common denominators. See if we can get things to factor. When in doubt, switch everybody back to sine and cosine. And see where we can go from there. Because at the very least, if we switch to sine and cosine, it gets us from 3 trig functions down to 2. Fewer choices. Okay? Questions on this guy? It's kind of weird and kind of gross. We've got a couple other kinds of problems, or at least one other kind of problem that they like to give us in this section. And I want us to talk through it because it's a little weird. And that would be things that look like this. Yeah, Polish is chipping in the corner here. So we're going to look at this one that says sine of 3 theta. So we've got a number inside our sine, equals negative 1/2. When we're looking at things like this, and they have pieces inside here, when we have to do these guys on the interval, ignore the on the interval part until we get to the very, very, very end. So we're going to treat it just like it said to find it for all possible answers until we get to the very, very, very end. So looking at something like this, we look at our sine of 3 theta, and I go, ew, I don't want to deal with 3 theta right here. Ew. We're going to do a u substitution. I want to get rid of it. I don't want to deal with 3 theta. I would much rather deal with u. So I'm going to swap a u for 3 theta. So if I write this as sine of u equals negative 1/2. That we can do. If sine of u equals negative 1/2, what options do we get for u? U could be 7 pi over 6 or 11 pi over 6. If we were asked to do this for all possible values, not on the interval, but all possible values, what would we put on there? Plus 2 pi n. We're going to put it. I promise. It's for a reason. I'm going to show you in a second. Plus 2 pi n. So because we have this u substitution that has these guys here, that has this number in here, that's why we're going to include this. Because what happens when we have our number inside here, think about when we graphed sine. If I had sine, it was very like wiggly squiggly. And if I did 2 sine or 3 sine, it made it skinnier. It made this horizontal compression where our coterminal angles that are going to have that same sine value happen more frequently. So we need to bring that period in so that we can find all the other angles that are going to have that same sign. So when we're dealing with a u substitution that has that b value, include the 2 pi n, because when we switch it back out of u to our theta, I'm going to look just at the 7 pi over 6 to start with. When we switch this back to our 3 theta, which is our 7 pi over 6 plus 2 pi n, and we want to get our theta by itself, what do? Divide by 3. So we're going to get that our theta equals, divide this guy by 3, we divide this guy by 3, we divide this guy by 3. What is 7 pi over 6 divided by 3? 7 pi over 18. And we got our 2 pi n over 3. Yep, 2/3 pi n. Or 2 pi over 3n, or 2 pi n over 3. I don't care how we word it. So this took the period of our sine that's normally really long and shrunk it down quite a bit. So what we're going to do is I'm going to look at that specific statement, and we're going to see how many places that is inside our unit circle. So what we're going to do is we are going to plug and chug integers in for n to find all of our values that are true. So what I'm going to do that's going to make this a little bit easier to do, I'm going to get these guys to common denominators. So I'm going to write this statement as my theta equals 7 pi over 18 plus common denominator, we need to multiply both by 6, 12 pi n over 18. So our first option for theta, if n is 0, basically, we're going to have our 7 pi over 18. That's the first guy. So then we're going to say if n is 1, so 7 pi over 18 plus 12 pi over 18. 7 plus 12 gives us 19 pi over 18, which is, in fact, still in our range here. It's still inside this 2 pi. It's less than 2 pi. So let's do it again and see if we're still inside that 2 pi. So 7 pi over 18 plus 2 sets of this. So you can do 7 pi plus 24 pi, or you can do our 19 pi plus 12 pi. We're just looking for all of these repetitions that keep going.
Why are we doing this if we're only supposed to be in the interval?
Because have we hit 2 pi yet?
No.
So let's keep going until we do.
Oh.
So if I add another 12, it gets us to 31 pi over 18. Is this still inside 2 pi? Yes. If we add another 12 pi over 18,
No.
because that would put us at 43. 43 pi over 18 is outside our interval. So all three of these are on our unit circle. They're gross, but they're there. So we need to make sure when we have these kinds of pieces that we find all the angles that fit in. So if we have one of these b values or a number inside our trig function, set it up like I ask you to do for every possible one, and then we're going to have to do a list at the end. So we're going to practice it again on the right guy when we switch back for our 3 theta on our 11 pi over 6, just so we can see it again. So swapping out our u for our 3 theta over here, we get our 11 pi over 6 plus 2 pi n. Getting our theta by itself, dividing everybody by 3. We get that our theta equals what? 11 pi over 18. 2 pi n over 3, which means we're doing that same kind of common denominator situation. So we're going to have that our theta is going to be our 11 pi over 18 plus 12 pi n over 18. You don't have to write that step. I find that much, much easier to do that as repeated addition than to have to figure out that common denominator each time. Your brain, your choice as to if you do that written out that way. So our options on theta over here, I'm going to take this dark purple. We've got our 11 pi over 18. Then I need to take, and we're going to do this addition, so our 11 pi over 18 plus the 12 pi over 18. So 11 plus 12 gives us 23 pi over 18. That's still inside my 2 pi. If we add another 12, 35 pi over 18. That's still inside my 2 pi. If we add another 12, are we still inside our unit circle? No. Nope. So that's where we stop. These are our possible answers. So when there's the number inside the trig function, it can make our fractions super messy and ucky. If we have a number inside here, set it up like we do for everything and then make a list at the end. It's awkward and weird.
And our answer would be the list.
Our answer is in the list. On the interval, our answer will always be a list that ends. If it's on the interval, that's when we're going to leave it as the little equations here. So on the interval, it's going to leave or on the all possible solutions, it gives us an equation. On the interval, we have a finite list. Okay. I'm good with that. Okay, that's everything that's in 7.2. That's everything. So that finishes out 7.2.
So the homework is done the day after the quiz?
Oh, I think I had it listed as the 26th so that it wasn't, in case we didn't get through everything we needed to, so in case we were still doing anything on Monday. But I was going to say, you can do everything on it. I just wasn't going to pull it forward. Like I say, the quiz is currently scheduled for Tuesday. I got to double check my calendars on stuff. So, but I can always push things back. I'm never going to pull something sooner because that's just mean. All right, so yeah. Happy Friday. Have a great weekend.